As I promised, I'm going to talk a little bit about the Warfarin Spectrum NMR and how to interpret it. Okay. First of all, I kind of want to give you a pep talk because I feel like people are a little discouraged because of the results in this lab. This was the first time we ever did this project full scale, and part of it went, I would say, sort of average for a first run through. And that was the part involving the 4-hydroxycoumarins. We learned a lot from it, and we're going to make a lot of improvements from it, and we're really interested in your results and anything you can report about it. Okay, any data you have, we're interested in that data. And remember, negative results are results. My expectations are very different from your expectations, and I think that to judge yourself as a failure or that you failed because you didn't get a warfarin product or a complete warfarin product, it's just not realistic in terms of what we were doing. We were doing higher risk work, and that means there were higher stakes, and that meant there was a greater probability that things wouldn't work. And even when we change some things next year, we're still going to gamble a little bit and do some new things. So this is always going to be kind of a frontier. It's not going to be some safe little haven where you're just repeating something that's been done before. So you were the first ones to do it, and that's kind of a privilege. Like I said, if I get my paper written this summer, I'm going to work some more on this summer. But if I get that written, you guys will, your class will have your names on the paper as long as you give me permission to do that. So I'm proud of what you did, and I think you should be proud. And as some people said, they didn't feel like they did enough work. You definitely did enough work. And some people told me that they didn't have, they have paragraphs that are going to be incomplete in their experimental section, and that's true. That is true. Okay. So is there some kind of problem?
No.
So just try to take a deep breath and realize that you did the best you could, and your best is good enough. You're not going to be like severely penalized for not getting all the products, and everybody got some products, so that's good. And a lot of people did get products. The other thing I wanted to say is that a lot of people are a little worried about the rough draft. We do not grade the rough draft. The rough draft is optional, and it's submitted to your instructor, okay? You probably want to submit it via Gmail or something like that, a Google Doc or something like that. We are not reading an entire rough draft. I personally read the intro. I look at the citations in the intro and the way you did the intro. I look at one of your experimental sections, so please include one complete experimental section if you can. And I look at, if you write a paragraph or so of the discussion, I would look at it, okay? But beyond that, I'm not reading the entire paper and rating the entire paper 2 times. I'm just not doing that. I've done it this way in the past, and it's worked well. Usually when I help people a little bit with format, they improve immensely. And generally, the papers are pretty good. Remember, the paper isn't going to be immensely long. It might be like 5 pages long, 6 pages long, and you might want to also attach your any spectra you have so that we can look at them. So I wanted to talk a little bit about the warfarin compound, the warfarin compounds that you've made, and why their spectra are complex, and where you can go to get information about warfarin spectroscopy, or the proton spectra of warfarin. Okay, warfarin is a very complicated molecule. It's certainly the most complicated molecule we've made in the course, and this is the structure of warfarin. Okay, and I will reiterate, although I'm going to write out the entire mechanisms that I covered over several weeks in lecture. I'm going to write these out and post these on Moodle. They are on Integrity. So realize if you came to class and you have Integrity, you actually already have all those mechanisms. I wrote out all the mechanisms of the aldol. I wrote out the mechanism of the formation of the 4-hydroxycoumarin compounds. And I also wrote out the entire mechanism of the catalysis over 2 weeks. I think I did 4 weeks of mechanism. So you have all this, and if you came to class, you would have all this right snug in your notebook, all right? But I am going to write it out for you guys. Realize also in the document that I gave you, there is all kinds of information, and in the papers that you have, there is all kinds of information about how to assign the spectra, okay? All right, so realize with the two compounds you couple together with the catalyst to make warfarin, those spectra should be assigned completely. However, the warfarin spectrum is going to be assigned a little more what I would call in a landscape fashion. In other words, you're not going to be like nailing down every single peak in the warfarin proton spectrum because it's really complicated. All right, why is it complicated? First of all, warfarin itself is a relatively complicated compound. It has 2 aromatic regions, and it has several different types of sort of sp3CHs in it. It has an OH, and this is like almost like a phenol in that it's an enol, which is like a phenol. And these tend to look in the IR and in the NMR more like carboxylic acids, and carboxylic acids show up at about 12 parts per million, okay? The other problem with warfarin is like a sugar in that it is constantly in equilibrium with a hemiketal form, 2 hemiketal forms. So what happens, very much like a sugar, and our undergraduate section, this is what we're studying right now. This oxygen here from the enol, and you might wonder, why do I draw it this way? In class I drew it with 2 carbonyls, but this is a situation where the enol would predominate, and the enol predominates because there is conjugation here, okay? So one of the carbonyls is existing in a keto form and the other in the enol form. The one that's the enol has an oxygen, and the oxygen will attack this carbonyl and open it up, just like a sugar would. Now, why is this so straightforward? Or so easy to do? Because this is a 6-membered ring, so if you count, it's 1, 2, 3, 4, 5, 6. Okay, and I drew this out because, I don't know, whenever I'm drawing the structure, it's a little complicated. Now, so this shows the attack. I've kind of like wrapped this around and made a ring. And this shows the oxygen attacking the carbonyl, opening it up. It's kind of simple carbonyl chemistry. Again, this is called a hemiketal, okay? And this is the charge separated form, and it's going to be in equilibrium with this form. So all I've done is moved the proton. It's a proton exchange, moved it from here to here. And the thing is, just like a sugar, just like there are alpha and beta anomers in sugars, like when you looked at glucose and fructose and you looked at the various aldohexoses, there are alpha and beta anomers, okay, at the anomeric carbon. This is really like an anomeric carbon, and there's really 2 ways the oxygen could come in. The oxygen could come in from the front, in which case the OH would go into the back, or the oxygen could come in from the back, in which case the OH would go to the front. So these 2 centers have opposite stereochemistries. Now, because you used a catalyst when you made warfarin, okay, you used a catalyst, and you used, I believe, the RR catalyst, you only made 1 stereoisomer. So interestingly, although warfarin is a very complicated molecule structurally, it only has 1 stereocenter that is constructed during the synthesis. But it is constructed stereo-specifically, or I should say very stereo-selectively with the catalyst. And we kind of described how that worked, and I'll write this out for you. But because you have a pre-existing stereocenter that's really of 1 form, the relationship between these 2 molecules is what? You should think about that a little bit. For example, I've drawn the R and the R here, but one of these is R and one of these is S. This one is the S, and this one is the R. So this is RS, RR, so what is the relationship between them, right? They are diastereomers. So these are diastereomers. Because they're diastereomers, they give different NMRs, okay? And they also form in different quantities. They're not in equal quantities. So it's very similar to what you learned about anomers. These are anomers, okay? And again, when this is sitting in solution, there's actually a relatively small amount of this and a rather large amount of these too, but there's more of one than the other. You're not expected to predict which one's going to be more than the other, okay? In terms of NMR, okay, there are two things I want you to look for, all right, to see if your reaction worked. The first thing I want you to look for are these methyl groups, okay? These will be called, I would call this like the methyl ketone, and this could be called the methyl ketal, okay? Methyl ketal. These two guys are around 1.5 and 1.7, and they will be singlets, okay? Whereas this one will be above 2, maybe about 2.1, 2.2 parts per million, and it'll be a singlet. They're all singlets. Now, this is the complexity of it. When you're looking at the NMR of this, you're not looking at one molecule, you're looking at 3 molecules. So just this methyl group alone gives 3 peaks, all right? I want you to look for those peaks. They're very distinctive looking, and when you have them, that's an indication that your reaction worked. The other thing you will see is a series of splittings between, say, 2 and 4 parts per million that represent these hydrogens. Here, these 3 hydrogens, and these 2 hydrogens and this hydrogen, and you might see these OHs as well, but these 2 distereotopic hydrogens, which are right here, it's kind of like the CH2 group, and right here, CH2 group, and the hydrogen next to the phenyl. They're kind of like in the middle of the spectrum, okay? The rest of it is all aromatic. So around 7, you'll see this cluster, okay? So that's kind of like a general topography. Like again, 1.5 and 1.7 and 2.1. These, okay, and they're all different. Okay, they're all different. That's what makes the NMR so complicated. These are different. I hope that makes sense to you that they're different, right? They're distereotopic. It's kind of that argument we've made along the way. But these two are different. They're going to split each other, and they're going to be split by that. So you're going to get some complex splitting there. But again, the splitting for these 3 occurs between, like, say, 2 and 4 parts per million, okay? There's a lot of little complex, like, doublets of doublets in there, okay? It's very hard to assign them without some help, okay? It's very hard to assign them, okay? These you'll be able to pick out very quickly. You'll be able to pick out the aromatic region, but you will not be able to assign it blow by blow, okay? So I'm just giving you like a little structural lesson here. And again, there's 3 of everything. There's 3 methyls. And, we thought this was interesting because it has this hemiketal. There's 3 of this hydrogen, there's 3 of that hydrogen, there's 3 of that hydrogen, and there's 3 of every single aromatic hydrogen and the OH. So that's why we didn't do integrals, okay? Because, for example, just this group of 3 hydrogens, the area is divided into 3 groups that are not equal. So it's like very complicated. It's a very complicated NMR. So again, what I want you to look for is this methyl, okay, 1.5 and 1.7. You should see 2, and they're not going to be equal height singlets. And then another one around 2.1, and they're small. Now realize these samples, because they've been kind of abused a little bit, frankly, and the abuse they obtained had to do with grease. Okay, we noticed that through the process, because you had grease in some of your glassware from over the year, you concentrated the grease into the vials. And in the NMRs, you're seeing like enormous grease peaks. Enormous, okay? Now I'm very remiss to erase this, but I'm going to erase this. And I just want to kind of give you a topography of the spectrum and tell you what to do. Like, I want you to be sort of resourceful with this and practical, okay? Do not become maniacs who feel like you have to nail down every peak, because that is not the way we're doing this, okay? It just has to kind of look like warfarin. All right, now, you may have some interesting features in your compound because you made analogs. If you can find those features in the spectrum, that's good too. For example, if your warfarin has a methoxy group in it, hooked into that chain, the chain that has, this has the coumarin part on it. If you have a methoxy group, look for that methyl group. You might be able to pick that out very easily. But again, you might have 3 of them. You might have 3 methoxy groups. If your warfarin structure, okay, has say a T-butyl group on it or something like that, you have a couple T-butyl groups on it, you might be able to pick those out. But again, you might have multiples of them. I think I've already seen this. I think I saw a spectrum where I saw multiple T-butyl groups because there's 3 forms of the compound. But you can try to pick those features out in addition to these other things. Okay, so generally, this is like the general discussion of it. Generally, what does the NMR look like? How do I know if someone made warfarin? What I see is like around 7. I just see a whole bunch of clusters. I'm being very dramatic here. I'm not like giving you like the exact shape, but I see a whole bunch of clusters of aromatics around 7. Okay? Then in between, you'll see all these like little doublets of doublets, working your way down to about 2. This is like between, there'll be little bunches of them, like along here. This is like around 2 to about 4. This is around 7. And then around 2, as I said, you see the singlet, which is the methyl ketone. And then just below 2, you see like 2 other peaks. And I don't remember the exact order. And that's kind of like what a warfarin spectrum looks like. And then again, if you had like a methoxy group, like at a 4, you might see a singlet due to the methoxy group. And if you had T-butyl groups, you might see singlets due to the T-butyl group way down, like at around 1 part per million. Okay, but there could be multiples of them. I don't want you to get into a wild blow-by-blow description. I can't say that enough. I know I'm being repetitive, but I know how you are. I'm like that too. I know. You're going to want to assign every single peak, okay? And it's going to be really, really, really hard to do. Okay, the other problem you have is some of you have very low yields. And if you have very low yields, okay, this is going to be just like rumblings in your baseline. And then you're going to have these enormous, horrifying grease peaks, okay? So what do the enormous, horrifying grease peaks look like? Okay. And this is something this is one of those things I really want to improve on next year because I wasn't happy with this. This is something I'm personally not happy with. It was the grease. Where's all, we've got to clean things up so we don't have this ridiculous amount of grease. And people have to clean their glassware a little better. But the grease is like, you'll see a giant peak like around 1, another one at about maybe 1.2. They're huge peaks. Then, usually water shows up, H2O. This is grease. Okay, H2O shows up at 1.5. We're seeing huge peaks due to dichloromethane because you didn't get it all off. We're also seeing, and then we're seeing, of course, the chloroform peak can be very big simply because your warfarin is so small. There's so little warfarin in there. So then we blow this way up, right? And then hopefully you see some stuff around, I'm sorry, this is like in the wrong, this is 7 here. But you see like some kind of little pattern around here that indicates you have the aromatics from warfarin. Then, you see some little doublets of doublets in here. And then if you're lucky, right, you'll see these 2 peaks that are due to the methyl ketal, and you'll see the methyl from the methyl ketone, okay? So I'm trying to give you like a sense of the topography in the context of being highly contaminated with grease, dichloromethane, chloroform, maybe even acetone, water. People have tons of water in these samples. Okay, so, another couple of weeks, we could get it pure, you could run it again, you'd get it pure, and everything would be a little bit better. Okay, but that's okay. What can you use to help you? Okay, well, one of the things that I guess people found a little disturbing, but this was a literature-based project. You didn't have a laboratory manual. You were supposed to look your procedures up, okay, which we've done for many years, but we've gotten a little bit of a rut, I would say, with our project. What can you use to help you? Go back to your papers. Why not use your papers to help you? For help in assigning spectra, I highly recommend looking at the green synthesis. The green synthesis paper that you got the procedure from. If you go to where you got the procedure from, there's information about the NMR. And they actually show a blow-up of some of these regions that I described, okay? The other thing that's extremely helpful is I gave out on several occasions these big fat packets of papers. I gave you those big fat packets to help you. I gave you a reading about how coumarins work, coumadins, which are warfarins, work. That came from a very famous medical textbook called Williams Hematology. You can look that up and reference that if you want to reference it, because that's where I got it from. And then I gave you a paper from Angewandte Chemie that was a really very well-written paper that had some very well-written experimental sections in it that I wanted you to look at and use. Some of the compounds are the same compounds some of you made, so why not look at their NMR interpretation and look at the level at which they interpret that. They take you through hydrogen by hydrogen, and you'll notice they don't really interpret every single aromatic. They just give a range for the aromatic and they just report it. And that may be the way you have to do some of this, okay? So there may be parts of those you can interpret and parts you can't. And then in your discussion, you can say something about the landscape being similar to the warfarin landscape, okay? So I hope that helps a little bit. All right, remember, in the writings that I've given you, there is information about how to how to write names for these compounds and so forth. And that packet that I gave you is just whopping with information that you can use to write this paper. There's even a paper there's a paper that kind of sums up all the various functions of warfarin. You know, that warfarin has antifungal activity, antibacterial activity, anti-cancer activity. So you can really get some good ideas from that on how to format that. And somebody, just another piece of advice, somebody said to me, they said, I feel like I'm copying other people's words and I'm plagiarizing. And the thing is with this, okay, especially if you're writing an experimental section, there's only certain ways you can say things. It's like there's a certain language and there's a certain way you have to say things. There's a format you have to follow. You might even be able to find a template for this paper. And I also want to state, I've had numerous people come into my office with these kind of weird examples of papers that they're following. You should be using the Journal of Organic Chemistry. That's what we went over in class. I spent 3 weeks in laboratory lecture, going over journals with you. And I was using the same journal every time. I was using the Journal of Organic Chemistry and I was using synthetic papers. I wasn't just randomly pulling a journal out. And that's why I gave you that packet, because it has some synthetic stuff in it. But you can go to the Journal of Organic Chemistry also for format, and you might be able to find a template somewhere for the Journal of Organic Chemistry. But the point here is, I suppose when you are doing an experimental section and you're following a very specific format, there's only a couple ways to say things. So you might feel a bit like you're plagiarizing, but this is not a place, I'm sorry to use that word, I shouldn't even use the plagiarize word. You're writing about your experiment, so it's not going to be plagiarizing, right? It's going to be your proportions, your experiment. But don't get into like really flowery writing in an attempt not to plagiarize. You've got to kind of follow a certain format and parts of it. The discussion section, right, that's going to be a little less rigorous in the way, compacted in the way it's written. As far as the discussion section goes, the people who don't have products, you're going to have to do a little more in terms of explaining why you didn't get product. What I'm going to do is, in addition to posting the entire mechanism again, I am going to write down some errors that I very definitely saw as the week went by, okay? And talk a little bit about why I don't think the 4-hydroxycoumarin reactions worked so well in some cases, okay? So we have some very definite ideas about that. But anyway, I hope that what I said about the NMR will kind of like put you in the right frame of mind for interpreting the NMR and not go too overboard. And again, use the paper that's from Angewandte Chemie, which is a well-known journal. Look at that paper where they used a different catalyst and they made some of these compounds. And you've made some other compounds, but look at what they did and kind of follow the way they did it. You know, kind of like follow the way they did it. They're going to have coupling constants and some stuff that you don't have. But just notice the way that they did it, the way they organized it, and the way they blended things together that they couldn't distinguish, because you actually can't distinguish the whole aromatic region. Okay? All right, so thank you for listening. I hope this helps a little bit. And I hope you understand how why warfarin does give such a complex proton NMR. In the future, we hope to do carbon NMRs of it, because the carbon will be a little simpler. Okay, so have a good weekend. See you in class.